So we discussed in our previous videos that the source of a magnetic field is moving charges. And if we have moving charges, we are creating magnetic fields. And those magnetic fields are going to have different shapes depending on, say, whether we have like a long straight wire that has moving charges in it, or a loop, or a solenoid. We're going to create magnetic fields. But then the big question is, okay, so we know that currents can create magnetic fields. What about the opposite? Is it possible for magnetic fields to create currents? And what Michael Faraday found was that a changing magnetic field can induce a current in a wire. So if this right here is a conducting wire, so it's made out of metal. If I were to run current through it, it would flow, okay? But this is an isolated wire. This is just a piece of metal in a loop. And he found that if you were to just put it in a magnetic field, nothing would happen. But if you change the strength of that magnetic field, what ends up happening is while the magnetic field is changing, you will induce a current. But once the magnetic field becomes constant, no current flows. So this idea that you have a changing magnetic field can induce a current in the wire is called electromagnetic induction. Induction, induce, cause. So there's different ways to do this. So in this case, we were looking at changing the magnetic field strength. If we make the field stronger or weaker, okay, if there's any change in the strength of that field, then there will be a current in the loop. So in order to understand why this happens, we have to talk about magnetic flux. Now, we previously talked about electric flux when we talked about Gauss's law and the idea that you could create this surface, this imaginary surface, and essentially calculate the electric field lines that are going through it. And then the more field lines that were passing through that surface, the larger the flux was. Well, there are lots of sources of flux. In this case, we're going to look at magnetic flux. So we're going to kind of walk through the same process that we did before. So picture that you have this imaginary sheet, and that rectangular sheet there has some number of field lines passing through it, okay? And that sheet has a surface area A. So if we were to double the magnetic field through that, I would have twice the flux because I'd have twice as many field lines passing through. If I was to make it smaller, then I'd have fewer field lines passing through. So there are lots of different ways to cause a change in magnetic flux. One is just to change the strength of the magnetic field. Others require motion. So for example, we can move a magnet closer or further from a loop of wire. We can actually move a loop of wire through a field. So we're going to take a look at some of those examples because these are some of the common ones. So let's say we're looking at this loop right here, and picture that this side of the loop, for your purposes, is coming straight at your eyes. So basically this loop is perpendicular to the screen so that the area of this loop is pointing to the right. So picture that that's what's going on here. So then what we're going to do is we're going to take a bar magnet and we are going to move it towards, right there. There we go, giving it a speed, and so it's moving towards, and that's going to induce a current while it is moving. So why does that happen? Well, moving that magnet closer is going to cause a change in the magnetic field strength, because where magnet here is going to have our magnetic field be strongest at the poles. Because if you remember that bar magnet shape, north, south, it comes out and around. Okay, and it's going to be strongest at the poles where you've got the kind of that convergence of those field lines, right? They're all coming in right here. So this is your strongest magnetic field. So what happens is that magnetic field starts out weak as that area being through the loop. And then as you bring it closer, the stronger field is there. And so moving that magnet in any way, shape, or form towards or away is going to cause an induced current. Now, the faster you move it, the stronger the current is going to be. And the direction you move it is going to determine which direction the current goes in the loop. Is it going to go clockwise or is it going to go counterclockwise? Now there's some laws to help us with that. So that's the first example. So in our next example, we've got a loop itself that moves into a region of the magnetic field. Now, we have to be careful on this one, and the simulations don't, like the little animations here aren't perfect. So what we have to remember going on here is that it's while the flux is changing. So if I have a loop here, when it's outside, no part of the area of this loop is actually in the field. So my magnetic field is that blue area right there. However, as I bring it closer, part of my loop is now in the field. Not high enough contrast on that one. So that would be my area. So as I bring it more in, more is going to be in. So I'm going to have that area there. So my area is increasing. Now, if I actually look at the location of the loop where it is right now, right here, okay, if I look at that, right as soon as that whole loop enters the field, in this whole area and all the locations of the loop from one end to the other, if the entire loop is inside that field, my area that's in the loop and the magnetic field, if they're constant, I'm not going to have a current. It's only while the loop is partially in, and the amount that is partially in is increasing or decreasing. So if I pull it through, and then I keep pulling it through, so then if I were to then keep pulling it through here, as soon as I start decreasing the amount in as I exit, then I'm also going to induce a flux. But while the loop is completely in the magnetic field, there is no change in flux, so therefore no current. I only get the current when it's moving into the area and out of the area. And in our last example, we're actually going to have a coil that is spinning inside of a magnetic field. While it's spinning, it is going to have a current. And so the reason that one's going to happen is because we have a magnetic field that goes from north to south. And so what's happening is the angle that our loop is making with that area is going to be constantly changing. And so as it's rotating and spinning inside of there, or alternatively, instead of spinning the coil, I could actually keep my coil fixed, and then I could put the magnets around it, and the magnets can spin. So anyways, in either way, if the angle that that field is making with the area changes, then you are going to have an induced current while that rotation is occurring. The faster the rotation, the stronger the current is going to be. So another fun example is like if I have like a solenoid here, and in this solenoid I'm changing the current in the solenoid. So if I got another loop here, then that is going to change the magnetic field. And so changing the current in the solenoid is going to cause a change in the magnetic field. But then what's fun is because that changing magnetic field through that loop, that's actually going to induce a current in that loop that originally didn't have a current. So there's all sorts of fun things that can happen. Of course, then that's going to change the magnetic field strength that is going through, because you're going to get an induced current, and that induced current can then also create a magnetic field, and then you get these kind of like competing factors going on. So the idea here is that an induced current is produced by changing the magnetic flux. That is the breakdown. There's lots of different ways for that to happen. Changing the area, changing the strength of the magnetic field, and changing the angle. So how much current can we produce? Well, Michael Faraday came up with the law of magnetic induction. This is the non-calculus version of this equation. So we use E, once again, for EMF. So this is our induced EMF, which is a voltage, remember, so EMF is a voltage, is equal to negative. The negative is going to be important. Remember, negative in physics really means opposite. Nope. It's all right. So that means opposite. And then N is our number of loops. So if you have one loop, you're going to get a certain voltage. a certain EMF. If you have more loops, you're going to get more of that. And then this last guy here, this is the rate of change of magnetic flux. This is the rate of change of magnetic flux. Because we said any change will produce a current, but what this is telling us is a larger rate of change is going to give us a larger EMF and therefore a larger current. So that magnetic flux in that rate of change is our BA cosine theta. So basically our change in magnetic flux over our change in time is going to be BA cosine theta over our change in time. But something here has to change. So there's different ways that this can look. So for example, if we keep our area constant and we keep our theta constant, we could write this as the change in flux over the change in time is equal to A cosine theta times the change in B over change in T. So what this says, this is the rate of change of the magnetic field. So it says I'm keeping area and my angle constant, but I'm going to change my magnetic field strength over time. So if I knew how fast that was happening, I could calculate my induced EMF. Or instead, I could say, okay, well, what if my magnetic field is constant, but instead I'm changing the area of my loop by like bringing it in or out of that field like we saw in that example? Well, then my B is what is constant, and then this would be my change in area over change in time. Or the most complicated of them would be the angle, because this actually kind of requires a lot of calculus to kind of handle that situation. But the other option is that I could have BA, and then I could have my change in cosine theta over my change in time. And that would be hardest for us to do without calculus. But those are the three different ways that we can induce this EMF. Okay, and then the negative sign is specifically telling us that the EMF produced opposes the change in flux. So if my flux increases, then the EMF, which produces a current, and currents create magnetic fields, it has to basically try and undo. Because my EMF creates a current, and we know that currents through wires create magnetic fields. So I'm going to get this induced magnetic field, and that induced magnetic field has to oppose the change. And that is kind of the most complicated conceptual part of this, is what does it mean by oppose the change? And there's a whole separate law for us to understand that one better. But you can do calculations pretty easy with the induced EMF. There'll be some examples for you later. And as I mentioned, how we figure out the direction of the induced current is something called Lenz's law. So Lenz's law is going to be able to handle this opposition. So Lenz's law says that induced EMF gives rise to a current whose magnetic field opposes the change in flux. So what we're picturing here is that we have a current loop. This is our solenoid. Okay, there's no power supply in this circuit here, but there is a resistor here. Okay, so we've got a resistor here, and for example, if I wanted to put a multimeter in place, like I could set it here to measure current, or I could set a voltmeter in place here and measure the voltage that's, passing through that resistor. I can do a couple different things. I can't do it with the solenoid, which is why I'd have to use it for the resistor there. What happens is I move this guy here and I change my magnetic field. What's happening is my flux is increasing because my magnetic field is increasing. So my flux increases. Well, Lenz's law says I need to oppose the increase. Well, remember that if I create a current, that current in a solenoid, currents create magnetic fields. So basically this induced, and this I here is induced. Like I said, that is being caused by the change in flux. So that is creating this current I. It's my I induced. That I induced is then creating a magnetic field. So these ones over here, these are for my solenoid. So if we use our right-hand rules for solenoid, this induced current is coming up and over the top out of the page and then coming back behind. So if you curl your fingers so they go into the page and then up out of the page, I can see that my thumb would point to the right. And the thumb is the direction of our induced magnetic field. Notice that that induced magnetic field is in the opposite direction as the magnetic field being produced by that magnet. It's opposing the change. Because my flux increased it, I needed my induced magnetic field to be in the opposite direction. That's what Lenz's law means. So you could simplify that down. I don't know if it actually helps in your head, but you could also say that any induction effect opposes its cause. So if the cause is causing an increase, the effect has to cause a decrease. If you have a decrease for your cause, the effect has to be an increase. They have to always do the opposite of each other. If there's an increasing flux, there's going to be a decreasing result. So why does this have to be true? It's conservation of energy. So because currents are essentially voltage, which are related to energy, current and voltage creates our energy. If we had an induced current, that would actually be like making a magnetic field stronger. Both the magnetic field and the current store energy, and that would mean that we would be adding an infinite amount of energy as it goes. But that's not what ends up happening. What ends up happening is if we try to increase the energy being stored in that coil, in the magnetic field, the magnetic field is going to have to decrease to oppose that change. So how do we determine the direction of the induced current? So these are steps that are used to find the induced current using Lenz's law. Don't skip these steps, okay? It's a process. I know there's quite a few steps, but the process of going through and analyzing each of these steps is what's going to help you come to the correct answer. Because man, if you can do Lenz's law, you understand most of the concepts relating to induction. The rest is just math. So the first thing you have to do is you have to determine the direction of the magnetic field through the coil. Like, so we're usually going to look at some sort of loop. Sometimes it's a square loop, but that's what we really mean by coil, is what is our conducting loop, okay, through there. So is there some sort of source, like this magnet? This magnetic field would be our B0, okay, so that's what we're talking about, the external source of the magnetic field. So we need to determine whether the magnetic flux is increasing or decreasing. So in this case, our magnetic flux through the loop was increasing. Then we have to determine the direction of the induced magnetic field. So you have to know where B0 is first. And then if your flux is increasing, our induced magnetic field must be in the opposite direction, because we have to undo the increase. We need to make our magnetic field smaller. If our flux is decreasing, our B induced must be in the same direction of B0. We actually need to help B0. If our flux is decreasing, we need to work against B0 if our flux is increasing. So we have to oppose the change. And then once you figure out the direction of B induced, you are going to use the direction of B induced to find I induced. So for example, if I figure out that in this square loop right here that my B induced must be out of the page to oppose the change, then I put my thumb out of the page, curl my fingers around. That tells me that my current has to flow counterclockwise through the loop. Whereas on the other hand, if for example for this loop I figure out that my B induced has to be into the page, then if I put my thumb into the page, then that tells me that my current would have to be clockwise. And that is the induced current. That induced current that is being created as a result of induction. Okay, so this is the order I go through. Determine the direction of B0. Okay, the external flux through the coil due to that magnetic field. Okay, is it increasing or decreasing? And then if it's increasing, where does B induced point? Opposite, because we need to work against B0. If your flux is decreasing, your B induced must be in the same direction because it has to help B0. And then once you figure out the direction of B induced, you figure out the direction of I induced. So we're actually going to try this out with some practice problems right here. So we're going to look at the first one. So we have to look at this situation. So this one says we have a north magnetic pole is moving towards the coil from above the page. So picture that your eyes are looking down at the magnet. So the north side of the magnet is down there. Your eyes are at the south side because the north side is into the coil. So because our north magnetic pole is moving towards the coil from above the page, so picture kind of like a side view. Your north is here, your south is up here, and it's moving down towards. So we have to remember that our B0 now is going to be into the page because our north side, our fields leave the north side of the magnet. So our B0 is into the page. This is my B0 going straight down like that. So I know that my field, due to that bar magnet, spreads out the further I get because it's strongest at the pole. So what's happening is that my magnetic flux is going to increase. So my magnetic flux is going to increase because my magnetic field strength is going to get bigger as that magnet gets closer. So that means I need to oppose. So I need my B induced to be in the opposite direction of B0. So because my B0 is into the page, I need my B induced to be out of the page. So now that I know that my B induced is out of the page, I can put my thumb in the direction of B induced, which is out of the page, use my fingers to curl, and I find that that is going to cause my induced current to be in the counterclockwise direction. All right, so that's the first one. So in this next one, I want you to pause it. I want you to try and think through it yourself and see if you can do it. All right, so I'm assuming you've tried this yourself. So in this case, we've rotated the magnet. So our coil there is still into the page, but now we have our north magnetic pole moving towards the coil in the plane of the page. So instead of going from top down into it, it's going to side. So on this one, our magnetic field, B0, is pointing towards the right. So if we look at our area vector, remember that our area vector is going to point like into or out of the page. Doesn't really matter which one you do. We usually do out of the page for A. But these are perpendicular to each other. So our flux is BA cosine theta. So they're at 90 degrees to each other. So cosine theta is 0. So there's actually no magnetic flux, which means no matter where I move this, whether I move it closer or further away, because my magnetic field and my area are perpendicular to each other, there's no flux. So moving this magnet in or out is not going to change anything. So there's going to be no current in this example. All right, what about another one? So we have this time we are pulling the wire through, and assume that the magnetic field only takes up the portion that is shown. Okay, don't assume that it takes up the entire page. So pause, see what you think. All right, assuming that you've paused and thought about this yourself. So our B0 would be out of the page because that's what the magnetic field is showing there. We've got our loop. So as we pull the coil to the right out of the magnetic field, if we picture what's happening in the next instant, my loop is going to be over here. So what's happened is the portion of my loop that is in the field has actually decreased. So because my area has decreased and my flux is BA cosine theta, this means that my magnetic field flux, or my magnetic flux, has also decreased. So in this example, because our flux has decreased, I need B induced to be in the same direction as B0, because I need to help the magnetic field. So in this case, my magnetic field that is induced, B induced, is actually also out of the page. So if I put my thumb out of the page, this is going to cause an induced current to also be in the counterclockwise direction, kind of like with our first example. So this is the big thing, is if your flux is decreasing, your B induced has to help B0, so it's going to be in the same direction. So in this case, we get a counterclockwise current. So try this one. Pause and see what you get. Okay, so I'm assuming that you've tried this one. So in this case, we have a coil that is getting smaller. So our A is decreasing again. So because our area is decreasing, our magnetic flux must also be decreasing, which we need our B induced to be in the same direction as B0. Our B0 is into the page, so we need our B induced to also be into the page. So if you put your thumb into the page, that's then going to cause a clockwise induced current. So we get clockwise. All right, one more here. So we have the loop starts into the page, and so it says we're going to do a vertical diameter. We're going to pull the left side, so this side here is going to come out of the page towards you. Our magnetic field is pointing to the left. Just kind of clarify that one. So pause it and see what happens as you rotate that loop. So I'm assuming that you've tried that one. So as it starts out flat and we are rotating it up towards us, we are starting initially with an area that would say point out of the page, but our magnetic field B, so that's actually going to be our B0, is to the left. So actually we start off with those perpendiculars, so our initial magnetic flux is 0. So as we start rotating that loop, that area and that magnetic field start to become more parallel. So as we rotate towards 90 degrees, our flux is going to increase. So since our flux is increasing, we need our induced magnetic field to be in the opposite direction. We need to oppose. We need to undo the increase. So our B induced is going to be in the opposite direction as B0. But this is kind of weird because our current in our loop, like, none of this is kind of aligned because we're rotating. So what I'm going to do is I'm going to picture that we have actually already rotated it so that our loop is here and our B0 is going this way. So you're kind of looking edge on again. So you're looking edge on at this. So if I picture that, so we've actually rotated it to 90 degrees. So we're no longer in the plane. We're 90 degrees rotated. So we've rotated it by 90 degrees. At this instant, this would actually be our maximum amount of flux. So if I need to undo the change, my B induced needs to be in the opposite direction of B0 when it's in this 90 degree position. So if I put my thumb to the right and B induced, my fingers are going to curl out the back and up towards the front. So they're going to curl up and out. So my I induced is going to kind of come up out of the page, back behind that. So if I was to then kind of flatten that again, my current is going to be coming kind of in this direction, because I'm going to need that B induced that is created in that loop. Oop, that didn't work out right. Apologize. Getting kind of a delay here. So that is going to be this counterclockwise direction. So that one's a little weird to kind of visualize because of it's rotating and changing angles at that time. So that then brings us to the fact that we are creating current. This is essentially creating electrical energy. We're converting some sort of magnetic field energy, motional energy, kinetic energy with these moving objects into electrical energy. This is what a generator is. So we talked about motors and the fact that we can use currents to create rotation with torque on current loops. We did that in our previous unit. Well, this is the opposite. A generator is taking motion and turning it into current. So for example, this is a little hand crank generator. So you've got this loop here. So once again, there's a whole lot of loops, because in order to get a good current, you need a lot of change in flux, and having a bunch of loops is going to do that. So you can actually then crank that. And as you crank that, there's a magnetic field here. So we've got our magnetic field coming out, and we're changing the angle. So as that's changing, we're going to get a light. And you'll see that the faster you crank, the brighter and brighter that light bulb would get. And you'll kind of see that in your lab this week. So a generator is going to be any sort of device that produces electricity from motion. And so if we think about our induced EMF, our EMF from Faraday's law was equal to negative N times the change in flux over the change in time. And then we can relate that to Ohm's law. Ohm's law says that our current is equal to our voltage over our resistance. So once you have found your EMF, you can divide that by the resistance in the coil, and that is going to give you the current, therefore, that was generated. But there's a bunch of different types of generators out there. So our generators to convert some sort of mechanical energy into electrical energy. And there's 4 standard ways that we can do this. We can rotate the conducting loop in the magnetic field, which is the one that we showed on the previous image. We can just move a wire in or out of the magnetic field. So if you've got your magnetic field in this area and you move that in and out, that's going to create a current. We can change the area of the loop while it's in a magnetic field. So that's the case here where we're like stretching it. Or we don't even need a loop. This one's kind of the weirdest. This one's kind of fun. It's actually really fun for calculus, but we're not doing calculus. If you've got this field right here, you don't even need a loop. You just need a conducting bar, and moving that conducting bar through that field is actually going to create a magnetic field. And you can use Faraday's law to find the amount of current that's generated, and you use Lenz's law to find the direction of the current that's produced. So let's look at our first example. So our first example is rotating a conducting loop in a magnetic field. So what causes our change in flux in this case is the angle between B and A changes. So A is coming perpendicularly out of the coil, and then B in this case is fixed. And so you have an angle that is changing. So you've got it changing right there. Boop, boop, boop. And if we use Faraday's law, in this case, you get E is equal to N, change in flux over change in time. Our flux is B dot A, BA cosine theta. And you would substitute in your BA cosine theta, but our B and our A themselves are actually constant. And our angle, by definition, is omega times time. Once again, we're not going to have to worry about where this comes from. I would derive it for you if this was a calculus-based class. But what ends up happening is that when you take that rate of change, we get the equation right here that was boxed, which has been here the whole time. But N is our number of loops, B is the strength of magnetic field, A is the area of the loop, omega, which shows up twice, is your angular frequency, radians per second. You probably saw the angular frequency in your 1401 class when you talked about oscillations. So it's basically your rate of change of the angle is really what that is. And then time. So those are the different factors. And it is based on sine. Why it switches from sine to cosine, from cosine to sine is a calculus thing with the derivatives, which you don't need to worry about. But this formula is on your formula sheet. So this tells us that the more loops we have, the stronger the magnetic field, the larger the area of the loops. And since omega is basically delta theta over delta t, it's our rate of change of angle over time. The faster you spin it, the faster it's rotating, the bigger and bigger the EMF is going to be. Now notice we took away the negative. This is just the magnitude of that induced EMF. We generally use Faraday's law in kind of in an absolute value form, and just to find the value in a lot of cases, and then we use Lenz's law to figure out the direction of the current. So our next example is when our flux changes because the area inside the magnetic field changes over time. We use this one a lot with a rectangular loop. It's a little bit easier with the geometry than a circle. So we have some sort of area, which is the full area of the loop, which I'm calling A0 here. And V is the speed at which it is being pulled. So at some later point in time, we are going to have a smaller area inside of the loop. So in this case, we're still using Faraday's law. We're still using the same definition of flux. And in this case, our angle, because our A would be, say, perpendicularly in or out. I guess in this case, we're defining our flux to be in the same, our area is going to be in the same direction as our magnetic field, which is into the page. But because our area is parallel, I guess this one's into the page, then our angle between those two vectors is 0. And so we get a 1 for cosine theta. So our flux is just B times A. Okay, we don't need to worry about the angle because A and B are parallel to each other. So then if you plug that in over here, in this case, we're actually keeping B the same. So when you do your change of BA, the B is actually constant. So we can actually pull the B out. So we get N B delta A over delta T. Notice I've gotten rid of the negative since I'm only worried about the magnitude here. And then we get the change in A over change in time. So if you wanted to derive this, basically you'd have to look at that speed V is really what we're trying to get into this here, because it's the speed at which it's being pulled through that we need to get into this equation. So if you define X to be the portion of the width that is in the field, area is going to be the length here, which stays constant, times X, the portion that's in the field. That's the area that is inside of the field right here. So if you plug that in, you get our change in A would be the change in L times X. But L is constant, so it can be pulled out in front. So you get that your change in A is equal to L times your change in X. You're like, well, why are we doing this? Well, the reason we're doing this is because we're going to introduce speed. So if you substitute that in, so sub in for delta A, you get BL times delta X. So what we have here now is delta X over delta T. And that speed is distance over time, is basically what that is. So what this tells us is that our induced EMF is equal to NBLV. So this is kind of cool, because this tells us that we just need to know the length of the portion that is in the field. We don't even need to know the whole area. Just what is the length of that side that stays constant? What is the speed that it's going through? And how many numbers of loops do we have? So the bigger the N, the bigger the magnetic field, the bigger L, and the bigger V, we're going to get a bigger induced EMF and therefore a larger current. So if I had chosen a smaller loop, L would be this portion of the loop. So if I pull it through at the same speed I was pulling this bigger loop through, I would not get as big of an EMF, therefore a smaller current. But if I pull this thing faster, the faster I pull it through, the bigger the EMF, the bigger the current is going to be. So the next one is changing the area of a loop. So it's kind of hard to stretch metal. So I kind of said, oh, well, what if you have like a slinky or something like that, and you can like stretch it out? Because it would be like a coil, right? You'd have like a coil for your slinky. You can make your coil bigger and smaller. That's really hard to do. So instead, what we tend to do is this is called a slide wire generator. So you've got these metal rails right here. That's what's back here, is like a metal rail. And then what you have is you have a conducting bar. So that's this other guy right here. You've got this conducting bar, because the bar goes all the way here. So that conducting bar is sitting on top of your slide wire. So you do actually have a closed loop. That closed loop would be here. So as you move the bar with a speed of V, the area that is being occupied here is going to increase. So that increases the area of the loop without having to worry about stretching metal. So you have your original area and you have your new area, and our new area is bigger. So the length L that we're going to talk about here is the length of the portion of the bar that is actually in the field. The part that's outside doesn't count because it's not going to be part of the loop itself. And once again, the speed that we pulled this through is going to matter. And if you were to do this derivation, same idea. You would have your V, you would have the portion, you'd have your delta X here, the portion that is changing over time. You'd be able to get your speed as delta X over delta T, and you get actually the same equation. And this one doesn't have the N though, because generally you don't have, it's one loop, right? Because it's one metal bar that is going through, so it's BLV. So our EMF is equal to BLV. We call this the motional EMF. You might see that term, because in all of these cases, the EMF is being induced by the motion of the bar. So this tells us that the longer the bar is, so if I was to make the loop wider here, so I could use this whole bar, if I could use the whole bar to make my loop, that would give me a larger induced EMF. If I could pull it faster, I would get more EMF. And if I had a stronger magnetic field, that would give me more EMF. Now, here's the funniest one. So that last example had a bar on a slide wire so that it made a closed loop. So we still had a loop. But even if there is no loop, we can still induce a current inside of this just metal bar, this conducting bar. Now, the reason is because inside of this bar, there are electrons. There's also protons. Remember, the protons are positive. They kind of stay in place in the structure, but our electrons are free to move. So what happens if I supply my electron with a speed V? Well, we know that our magnetic force is equal to QV cross B. So by moving that electron in a field, and my velocity here is in that field, and they're perpendicular because my B is pointing out of the page, I'm creating a magnetic force. So if you use your right hand, well, actually left hand rule, right? Because we are using the electron, I point my left hand in the direction of V. I rotate my palm out of the page so that it's facing up. That causes my thumb to point towards the top of the page. And the thumb is my magnetic force. When you do your FB is QV cross B. So those electrons are going to feel a force towards the top. Now the positive charges actually feel a force towards the bottom, but those don't move because they are fixed in the nucleus. So if we show this equation, what ends up happening when you start plugging things in is V cross B ends up just being VB because they're 90 degrees to each other. And then the charge of an electron is E, that's our elementary charge. That's the 1.6 times 10 to the negative 19 coulombs. So we're going to get a larger force, which would be EVB, with a faster speed and a stronger magnetic field. Now this is going to create charge separation. So the bottom of my bar is going to end up with a net positive charge, and the top of my bar is going to end up with a net negative charge. Now those positive charges haven't actually moved towards the bottom because they're fixed in the structure of the bar in the nucleus there. Only the electrons are actually moving. But we do get this separation of charge. Now, separations of charge create an electric field. The electric field is going to point from positive to negative. So there's going to be this induced electric field. And this kind of sets us up to be kind of like a capacitor, because your capacitor has your positive charges on one side and it has your negative charges on the other, and our electric field goes from positive to negative. So we get this voltage difference between the end created by this electric field. So the electric field then causes a force in the opposite direction. So because your electric field is QE, and your electric field is going to be in the opposite direction when you look at the magnitude on a negative charge. Because protons feel a force from the electric field in the same direction as the field. Electrons feel an electric force in the opposite direction. So you can see kind of here in green, I didn't create great contrast with this, I apologize, that the electric field then points towards the bottom. So your magnetic force on the electron is up. The electric force is down. So basically what's going to happen is that the electrons are going to move up towards the top until the magnetic and electric forces are balanced. So those electrons are going to move up until they reach balance. So at balance, our magnetic forces and electric forces are equal. So we said that our magnetic force was EVB. Our electric force is E times E. That's our elementary charge, 1.6 times 10 to the negative 19 coulombs times E. Our E actually cancels. Oop, there it is. And so we get that VB is equal to E. So our potential difference for a parallel plate is E times D. Okay, we did that for parallel plate capacitors. We also know then that is now going to be our induced EMF. So we're going to use the curly E for our EMF there. And then D is going to be L. That's going to be the length of that's the separation distance between the positives and negatives. So that's going to be L. So we're replacing D with L. And then our electric field is going to be E over L. Okay, that's how big the electric field is going to be. So if we substitute in, that gives us VB is equal to E over L. We replaced our electric field E with our induced EMF E. And if we solve for our induced EMF, we get that E is equal to, oh my gosh, BLV. So this same expression here for our induced EMF is based on the length of the conductor, the magnetic field strength, and the speed at which it pulls through. So those last three examples all have the exact same expression, except for we had one that had an N in there because you could have lots of different loops. So this is our motional EMF. So this is used in a lot of situations.